Hello students, today we will be learning about propagation of light through optical fiber. This particular topic is very much connected to your branch, that is electronics and communication engineering, because optical fibers are mainly used for communication purposes. This has made a very big change in the way of communication. It has facilitated the optical signals to be sent as information through optical fiber. So, such an important topic we are going to learn today. So now we will learn about the principle of light propagation through optical fiber. Okay, so we have seen in the class that the basic principle is to attain total internal reflection. Okay, when the light ray is incident on the interface between two medium having different indices at an angle greater than the critical angle, the light gets totally internally reflected within the medium of higher refractive index. So this is the basic principle. We will see how it is achieved. So here you can see this portion, no? This is so this is core and this is cladding. Core is having the refractive index N1 and this is having the refractive index N2. So at some random angle of incidence, I am sending the ray light. Then we can understand with the help of the relationship between the refractive indices between the core and cladding that the light ray is actually traveling from denser to rarer medium. So it will move away from the normal, that is refracted ray will move away from the normal. So part of the ray will get refracted and part of the ray will get reflected. So the one which is refracted, no, that will move away from the normal. So now if I suppose increase this θ1 to a little greater angle, then what will happen? The refracted ray will move little further away from the normal. So as I keep increasing the angle of incidence, this θ2 will also keep increasing. So for one particular angle of incidence, this θ2 will become 90 degree, which means this refracted ray will coincide with the interface between the core and the cladding. So the corresponding angle of incidence is called critical angle. Okay, so critical angle is the basic requirement for achieving the light to propagate through the optical fiber. Now what will happen if suppose I increase the angle of incidence greater than critical angle? So what will happen? This ray which is already coinciding with that of the interface will completely go away from the normal and enter into this medium itself. So which means total internal reflection will take place. That is the principle of propagation. Okay, so let us go to the next picture and try to understand further. So here what is shown is the angle of incidence is equal to θc. So which means critical angle. So what happens? From the normal, the refracted ray makes the angle θ2 is equal to 90 degree, which means it coincides with the interface between core and cladding. So anything greater than θc will make complete total internal reflection possible. Now we will have to derive an expression for this θc. Okay, so we will go for the derivation. So you are going to apply Snell's law for it. Okay, so Snell's law is nothing but product of refractive index of one medium multiplied by sine of angle of incidence is equal to refractive index of the next medium, second medium, multiplied by sine of angle of refraction. So n1 sine θ1 is equal to n2 sine θ2. Okay, so when θ1 is equal to θc, θ2 becomes what? 90 degree. Just now we saw in the picture. Okay, so when I substitute that, that here, what will I get? N1 sine θc is equal to N2 sine 90. So sine 90 is 1. So I will get sine theta c is equal to n2 by n1. So which means theta c is equal to sine inverse of n2 by n1. So this is the formula for finding out critical angle. Okay. Now next parameter is numerical aperture and acceptance angle. Now this is the whole of the optical fiber. That is, this is the whole of the optical fiber where you are having core and cladding, and you can see the interface between core and cladding here, first interface. After that, if it once again hits here, once again it is core cladding interface. Okay. Now here we have to achieve critical angle or greater than critical angle is already known to us. Now what has to be also taken into account is the ray is coming out, coming into the optical fiber from outside. So there is one more angle of incidence which is responsible for the propagation of light through optical fiber. So here I have to maintain critical angle or greater than critical angle, means accordingly the angle of incidence have to be adjusted here. So only then I will be able to get the critical angle here, so that I will get total internal reflection. No part of the information will go into the cladding and get wasted. Okay, so that is the concept. So here I assume the refractive index of the outside medium to be n0, and this is n1, and for cladding it is n2. Okay, so the light travels from now rarer medium to denser medium, so automatically it goes closer to the normal. So this is the normal. Axis is the normal. Fiber axis is the normal. Okay, so with respect to the axis, the angle of incidence I am taking it to be theta notch. Okay, angle of incidence I am taking it to be theta notch. Then it moves inside, so this angle I am taking it to be theta r. Then it hits the interface between core and cladding. Okay, I do not know what this angle is, but I assume that it should be critical angle. Only then it will be coinciding with the interface. Only then I can make sure that only total internal reflection is going to take place. Okay, so let us write some equations. Once again I will apply Snell's law. So when I apply Snell's law between the outside medium and the core. So this is between outside and core. Okay, so n0 sin theta naught is equal to n1 sin theta r. Okay, so sin theta naught is equal to n1 by n0 into sin theta r. Now I can write basic equation sin square theta plus cos square theta is equal to 1. So sin square theta is equal to 1 minus cos square theta. So sin theta is equal to square root of 1 minus cos square theta. Okay, so I will substitute the sin theta r as square root of 1 minus cos square theta. Okay, so sin theta naught is equal to n1 by n0 square root of 1 minus cos square theta r. Now I will apply Snell's law between core and cladding as usual. Okay, so n1 sin theta 90 minus theta r is equal to n2 sin 90. So sin 90 minus theta is nothing but cos theta. So cos theta r is equal to n2. So from this I can write cos theta r is equal to n2 by n1, which I can substitute here. Cos square theta r. Okay, so we will see it in the next slide. So sin theta naught is equal to n1 by n0 square root of 1 minus n2 by n1 whole square. Where cos square theta r is there, I have substituted n2 by n1. Okay, then I am taking LCM. then I am simplifying. If I bring this N1, see here, if I can write this like this, N1 by N0 into, I bring this N1 outside, so it will N1 square outside the square root, so I will get it as simply N1 square root of N1 square minus N2 square. So this and this will get cancelled, so I will get this one, square root of N1 square minus N2 square whole divided by N0. Suppose if I assume the outside medium to be air, then sin theta naught is equal to square root of N1 square minus N2 square. So theta naught is equal to sin inverse of square root of N1 square minus N2 square. So this theta naught only is the acceptance angle. So this is the expression for acceptance angle. So when I calculate critical angle or when I calculate acceptance angle, you have to observe that it is only in terms of refractive indices of core and cladding. So if I make proper adjustment of the refractive indices between the core and cladding, I can easily fabricate optical fiber and also make sure that the light travels only through the core medium, ensuring total internal reflection. So with this we will move on to the definition of this acceptance angle. The maximum angle at which the light suffers total internal reflection is known as acceptance angle. So ray enter through the cone as shown in the figure is subjected to the total internal reflection in the core and hence reach the other end of the fiber. Hence this cone is called acceptance angle. Now at this point you should remember that acceptance angle is the maximum limit. That is, if you cross above theta naught value, you won't achieve critical angle. You will go down. But if you are lesser than acceptance angle, then you can go above critical angle, ensuring total internal reflection. So this has to be understood. So acceptance angle is the maximum limit. Okay, critical angle is minimum requirement. So this basic difference has to be kept in mind, and this is between core and cladding, and this is between outside medium and core. So these things should never confuse you. So with this we will move on to the next parameter, that is numerical aperture. So what is numerical aperture? Technically speaking, it is the sign of the acceptance angle of the fiber. That is, NA is equal to sin theta naught. But actually speaking, it gives the light gathering capability of the fiber. So very important, how much of information has to be sent through the optical fiber can be understood with this. So NA is equal to sin theta naught. Sin theta naught just now we calculated as square root of N1 square minus N2 square divided by N0. So NA is equal to square root of N1 square minus N2 square. That is theta naught, we calculated it as sin inverse of square root of N1 square minus N2 square by N0. This is what we calculated. Now what we want is sin theta naught. So sin of sin inverse square root of N1 square minus N2 square divided by N0. This sin and sin inverse will get cancelled. I will get only N1 square minus N2 square whole divided by N0. That is my sin, that is my NA. That is my NA. Okay. So that is what is here. Okay. Now we'll go to the next parameter. So next we will calculate fractional index change. So this is something like efficiency. Like that is, it is defined as the ratio of the difference of refractive indices of core and cladding to the refractive index of the core. So how much difference if you maintain how well the propagation will take place is given by fractional index change. Okay, so delta is equal to n1 minus n2 divided by n1. Now simplify it by cross multiplying. So n1 into delta is equal to n1 minus n2. So now what do I know is numerical aperture NA is equal to square root of n1 square minus n2 square. Just now we saw, assuming the outside medium to be air, I will get this expression. So this is something like a square minus b square. So which can be expanded as a plus b into a minus b. Okay, so n1 plus n2 into n1 minus n2. So what do I write for now? n1 minus n2 from this equation as n1 into delta. So I substitute in the place of n1 minus n2 as n1 into delta. Now I assume n1 to be approximately equal to n2. So what will I get? This n1 and this n2 are approximately same. So I assume it to be simply n1 itself. So 2n1 I will get. So square root of 2n1 into n1 into delta. So I will get 2n1 square delta square root of. So I can write this as I will take n1 outside into square root of 2 delta, that is Na. So this is the relationship between numerical aperture and the fractional index change. So let us see the summary of what we have learnt. The principle of propagation of light through optical fiber is total internal reflection. When the angle of refraction of the ray is 90 degree, the corresponding angle of incidence is called the critical angle, which is denoted as theta c. The acceptance angle of the fiber is given by theta naught is equal to sine inverse of square root of n1 square minus n2 square. Here we are assuming the outside medium to be air, so n naught is treated as 1. The numerical aperture is defined as the sine of the acceptance angle of the fiber. So it gives the light gathering capability of the fiber. So Na can be written as sine theta naught. So this is the summary of what we have learnt. Thank you very much. We will meet in the next video lecture.